Okay, welcome everyone to another Astronomy on Tap. Thank you all for coming out. So we have a pretty exciting day tonight. We're going to be talking about galaxies and pulsars. Plus, we're going to make well, I'll let Jacob introduce the drink. I don't want to spoil the name. So if this is your first time coming out to one of our live streams, the way it works is we're going to have a brief demo of how to make your astronomy themed cocktail, followed by our first talk of the night, which tonight is going to be Sinclaire Manning and how to lose a galaxy in 10 to the 12.7 days, followed by trivia, astronomy in the news, and then we're going to learn about pulsars with Grayce Brown and Thomas Nguyen. Come back for trivia answers after that. So I'm going to go ahead and let Jacob get started on this. Jacob, show us what you are making.
All right, so hopefully if you saw those things scroll by and you happen to have those ingredients and you didn't see it beforehand, or you did see it beforehand, you have all the ingredients. If not, save this one and so you can make it on your own at home sometime. But what we're gonna be making is we're calling a Mars-garita. So it's a twist on a normal margarita, but Mars themed. And basically what that means is we're going to be making it red. So if you noticed from the ingredient list, we have some strawberry margarita mix, just add tequila and some cranberry blood orange juice, and that's going to give it a nice red color. So to start off, we're going to start off with our tequila. We're going to take 2 ounces of this. Now, if you want to, if you don't have 2 ounces easily, you can just do a shot glass as well. That'll be a little bit less, but it'll be in an even amount. So everything's basically in increments of this unit, 2 ounces. So we're going to do 2 ounces of tequila, and in this case, I'm using the gold just to give it a little more orangey color, a nice Mars color. Again, we've built this drink just around the name Mars-garita to make it red. And then, so we're gonna add 4 ounces of the strawberry margarita mix, or 2 shots if you're doing shot glasses. This will give it a nice strawberry. So that was 2, and now 4. All right, and if you don't happen to have the cranberry blood orange juice, you can just do 2 more ounces of the strawberry margarita mix. But if you did happen to find cranberry blood orange juice, then you'll use 2 ounces of that then. You can see already how it's getting nice and red. And now comes the beer. One of the themes that we've been doing to keep the on tap is to make it sort of a beer tail, or a beer as one of the bases in the drink. And so we're going to use this Fresh Haze IPA from Deschutes. If you don't have this, you can use some similar citrusy, orangey IPA, and we're going to use 6 ounces of it. So just half of the can here. And if you did the shot glasses, maybe you want to go a little less than half, make it not quite as beery, a little more margarita-y. And so I'm just going to eyeball this. It doesn't have to be exact, maybe a little more. All right. And then lastly, we're going to add in some lime. So we're going to use the juice of a whole lime. So we're going to cut that bad boy in half. And if you want to cut it long ways to save a little bit for a garnish, that's what I'm going to do. So I'm going to cut just a little slice off the edge, set that aside for later. And then, oops, I didn't get this out ahead of time, but my juicer, we're just going to squeeze it right in there. And so what we've really made is in essence, a fruit punch margarita. There's a lot of fruit flavors in here, some orangey, some strawberry, some cranberry, some blood orange, and then some lime. So it's got a lot of citrus and strawberry flavors. And so it's, yeah, just kind of a fruit punchy margarita. Yeah, all right. And so that's everything. And now you top it off with ice, but it wouldn't be a true Mars-garita without a secret ingredient. And for that, I'm gonna get my tongs and my gloves because you don't wanna handle this with your fingers. I've got a bag here of dry ice. And now this is a Marsgarita, true Marsgarita, because in case you aren't aware, the caps, the polar caps on Mars are covered in dry ice actually. And so for part of the orbit, they're in complete darkness, and the carbon dioxide turns into, it solidifies, turns into dry ice. And then, when it warms up in the other part of the orbit, then it sublimates, which means it goes directly from a solid to a gas. So there's no liquid in between. These are big pieces. It's going to take a while for them to go away. But here's what happens then when you add that in. You get some nice bubbling effect, and it goes right to the bottom, just like a true Mars polar ice cap. So here's, and again, I should warn you that if you make this at home, do not drink or touch or handle the dry ice. Hopefully this doesn't bubble over. I didn't actually try this with beer before. I tried it with water and it seemed just fine. Seems like maybe things are going a little haywire here, but looks pretty good, nice and foggy. I'm gonna give it just a quick little sip because all the ice should be on the bottom. So cheers, Michael. Here's our Marsgarita.
Cheers, Jacob, Arvin. That was absolutely fantastic. I don't have any dry ice, but it's still pretty good. I like it.
And if you're in the State College area, you can just go on to Berkey Creamery and get some dry ice. That's what I did earlier this afternoon.
Did you tell them what you're going to be using it for?
No, I actually just bought some ice cream and was like, oh, can I also get some dry ice? And that's usually what it's there for. So I wanted ice cream too.
Awesome.
But, yeah.
All right. Well, thank you very much, Jacob, for that. And since also, you got the tequila, you got the limes there. If you want to do a few shots during the show, feel free to do that too.
No, I should mention that. Now, remember, this had 2 ounces of tequila and half a beer in it, so it's a sipper drink. You don't want to drink it too quickly.
All right. Stay conscious for the talks. We want you to be able to see that. All right. Thank you, Jacob. So I think we're ready to go ahead and get started with our first talk of the night. So all the way from Texas, the Sinclaire Manning, aka Major Merger. You are going to be telling us all about star-forming galaxies. Take it away.
Yeah, thank you so much for having me. I love doing Astronomy on Tap. I've been doing Astronomy on Tap in Austin for quite a while. So this is my first virtual experience though, so see how it goes. But yeah, so I'm going to be talking today about galaxy formation and evolution on a kind of a broader scale. My title is a little more specific than what I'm actually going to be talking about. But I had to come up with a cute title. And because I'm from Austin, I feel like I have some contractual, I'm not from Austin, but I've been living there for the past 5 years. I have some sort of contractual obligation to reference Matthew McConaughey in some way. And so some of you may have seen this not so great rom-com that my title is based on. Would I recommend it? I don't know. But anyway, moving on to the science portion of the talk. I work on dusty star-forming galaxies. I'm a 6th-year PhD student at UT Austin. And so, all right, let's just jump right into it. And I apologize for that. So when talking about galaxy evolution, I find that the best thing to do is to first start off with really pretty pictures, kind of lure the audience in, and then disappoint them with the images that you actually look at on a daily basis. So the best galaxy picture to look at, in my opinion, and in many extragalactic astronomers' opinion, is the Hubble Ultra Deep Field. So that's what was on the title slide, and that's what's here now. And so in the Hubble Ultra Deep Field, this is 11 minutes, a little over 11 minutes of the Hubble Space Telescope staring at a patch of sky. And in this image, you get over 10,000 galaxies. So basically every dot you see in the image is a galaxy, with some exception to a few foreground stars. But basically what someone might do when they see this image is try and classify the galaxies based on what they look like. And that's more or less what Edwin Hubble did when he was looking at galaxies, well before the invention of the spacecraft, of course. And so what you might see though when looking at this image are some spiral galaxies, which are in the pink boxes, which are clearly have these kind of well-defined arms spiraling out from the center. They're kind of disc-like. You can also see what are called elliptical galaxies, which are redder and kind of fuzzier and just kind of have these spherical elliptical shapes. And so, yeah, if you were Edwin Hubble looking at galaxies like this, you might try and make sense of them, make some sort of evolutionary picture based on the things you see in the sky. And that is more or less what he tried to do. And so in 1926, Edwin Hubble came up with this classification scheme, which we know as the Hubble tuning fork. And basically you see the ellipticals on the left kind of merging or evolving into spiral galaxies on the right. And it's stuck around for quite a while. I mean, he did this in the 20s, and even to this day, because he thought that ellipticals formed first and then later morphed into spirals, ellipticals are called early type galaxies and spirals are called late type galaxies. And we still call them that, even though that's not how we think it works anymore, but we just like making things confusing for ourselves. So then in the late 50s, we had a bit of an expansion upon the Hubble tuning fork with Gerard de Vaucouleurs. And so it's more or less the same tuning fork, just now with more galaxy types. So he included intermediate spirals as well as dwarf galaxies and irregular galaxies, which really had no place on the tuning fork in terms of evolution. And so he just kind of stuck them to the side. But yeah, so like I mentioned, even though this is the historical picture of galaxy evolution, we actually think it's flipped now. So from right to left, or left to right, sorry, I don't know what language I'm reading in. Left to right, it looks now like this, where we think spiral galaxies or regular galaxies can form, and then through various mechanisms, they will actually evolve into elliptical galaxies. And I'll get more into those processes and how we think that happens in a little bit. Okay, so now a slightly more advanced picture of galaxy evolution, combining all the new knowledge from our fancy spacecrafts and what astronomers have been doing for the last several decades. We have this updated picture. So I've tried to color coordinate it to make it a little clearer, since there are a lot of things going on in this diagram. But so basically, starting from the lower left, you have an isolated disk or an isolated spiral. And you could intuitively think, how could I make an elliptical galaxy, some massive kind of amorphous blob of a galaxy? And if you crash two disk galaxies together or two spirals together, they might form that kind of blob. And so that's what we think actually happens. If you go up to step C, the interaction and merger stage, you have two equally mass or similarly massed spiral galaxies coming together and beginning to merge. And then because of that merging, you've got two basically wells of fuel to use crashing into each other. Double the fuel means double, if not more, star formation. So more fuel to form stars leads to this bump in star formation. And that's what you see in the graph as well. So you start out kind of, a spiral on its own can form like 10 stars per year pretty regularly. And then if you crash them together, you'll see this significant jump, and you'll get, hundreds of solar masses per year being formed. But eventually, you use up all that fuel, and supernovae are going off, they're blowing out gas, you lose the definition of those nice spiral arms, and then you're left with a quiescent elliptical. So those are called known as red and dead galaxies. So no more nice blue stars to make up that blue and white light. You're left with an older stellar population to get these redder galaxies. And really, there's not much going on in them anymore. So hence the red and dead, which is a little harsh in my opinion, but that's what we call them. Okay, so One thing to note, though, that was a major merger picture, which is where my AOT name comes from, in case you were wondering. But yeah, so that was the picture of a major merger, so which is what's depicted in this very high-tech diagram I've created for you, where you have two spiral galaxies, you add them together, and you get one bigger elliptical galaxy. But another thing that can happen is you might have a spiral galaxy, and instead of another massive spiral galaxy nearby, it might have a few satellite galaxies or a few dwarf galaxies around it that are much smaller mass. And so the bigger galaxy can gobble up those smaller galaxies, but because they don't have the gravitational well and force to really destroy the spiral structure, it can just absorb those smaller galaxies, still get like a bump in star formation, and just become a bigger spiral galaxy. And that can happen with irregular galaxies too, or even ellipticals can become bigger ellipticals just by consuming the smaller things around it. And there's some really lovely names for that, like galactic cannibalism, which I don't know how we come up with this stuff, but so really the thing that makes the difference for whether or not you're going to be having these major or minor mergers comes down to the environment of the galaxies. So, for example, our Milky Way, which we think is a spiral galaxy, exists in the local group. And in the local group, we have our Milky Way, and this is on the diagram on the left, the Milky Way and the Andromeda Galaxy, which we know is a spiral galaxy, and the Triangulum Galaxy. So these are three decently sized spiral galaxies, but everything else in the local group is a dwarf galaxy or a satellite galaxy. So really small things that aren't going to have much impact on the three major players in the local group. So yeah, even there are about 80 members total that we think of in the local group. And yeah, they're all pretty itty bitty guys. But now if you think of something like the Virgo cluster, which is on the right, this is a cluster of dozens of bright, large, massive galaxies. And you can see in the image these huge ellipticals kind of sticking out, several of them. And so in a cluster like this, you've got 30 bright galaxies and on the order of 1,500 members, which includes all the dwarfs and satellites and stuff. So you've just got a lot more things that are in space that can potentially latch onto each other or get pulled in by the other's gravity and collide and coalesce and interact. And so that's going to allow for the development of a lot more ellipticals, whereas in our local group, because our Milky Way is pretty isolated, it's been able to stay a nice spiral galaxy for billions of years. All right, so just to drive home the point of mergers a little bit more, you might, since we're only able to see a galaxy at one given point in time, because humans, we only exist on this earth for 100 years if we're lucky. So what astronomers do is you look at a lot of different galaxies and try and piece together an evolutionary picture that makes sense with our computational models and observations. So this is a nice video I like to show, and it starts with a galaxy evolution model, a computer simulation. And then every now and again, it'll stop to show you a Hubble Space Telescope image of two galaxies that fit that model. So you start out with the beginning stages of an interaction, kind of first passage, two disk galaxies starting to collide together. And then every now and then you get a very cool real picture. So I'll just let this play out, let you enjoy it. You start to see these signature tidal tails come out from the sides of the galaxies. That's due to the effects of gravity of these two massive systems coming together. These tidal tails get swept out, leaving these long trails of stars and dust. And then an important thing this video shows also is how important the orientation is of what we're looking at. We only get one angle to look at stuff from our point of view on Earth. And so something that you could just be looking at a edge-on galaxy that doesn't look like a whole lot, but if you had a different angle of it, you could see that it's a spiral galaxy. So those are effects like that are things we have to keep in mind. Okay, so thinking about major mergers and the types of galaxies or systems that that collision produces locally in the local universe. And I'm using the term locally very loosely here. By locally, I mean within the last 8 billion years, which is the same as saying below redshift 1. So for excal people, that'll seem like low redshift and local. But so locally, we know that major mergers are the cause of these luminous infrared galaxies. And so the mergers explain their high luminosities. It explains their increased star formation rates. So it's greater than 10 solar masses per year about. But if you go to higher redshifts, which is the work that I look at, so greater than redshift 1, so within 6 billion years of the Big Bang, so the universe is 13.6 billion years old, give or take a few. And so within 6 billion years of the Big Bang, all star-forming galaxies have about a 10 times higher rate of star formation just across the board. And so in that sense, mergers aren't necessarily required to make these what are considered extreme galaxies in the earlier universe. So we kind of want to get an idea of, well, if it's not mergers, is it something else causing them? Or maybe mergers are still really important. They're just really hard to detect when you get farther and farther away. So, so this brings me to dusty star-forming galaxies, which is stuff I work on. And these are considered to be pretty extreme systems. So their luminosities are similar to those luminous infrared galaxies that I just mentioned, 10 to the 11, 10 to the 12 solar luminosities. However, they are much farther away. So as I said, these exist 1 to 6 billion years after the Big Bang. They're also have much higher star formation rates. So they can form 100 to 1,000 solar masses per year or more. There are some that form, 2,000 solar masses per year. So the issue, though, is when you get farther away in space, trying to observe things gets harder and harder. And so because of that, the physical characteristics of dusty star-forming galaxies are not super well understood. So this is the image on the bottom right, which kind of illustrates that point. This is from my advisor, Caitlin Casey's work last year. So this is an ALMA image, or the Atacama Large Millimeter Array. It's an array in Chile. On the left is the image from ALMA, and on the right is an artist's impression. And this galaxy exists at redshift 5.8, which is just a little over 1 billion years after the Big Bang. And you can see, like, what can you tell about this galaxy? It's blobby, it's it's red, but you can kind of make out that there's a second kind of smaller companion to the south. So maybe that is indicative that there's two systems that are interacting, and that's causing the increased star formation. But you're not going to see any spiral arms at redshift 5.8. Or even signs of previous merger, like those tidal tails, are just going to be way too faint to try and observe. So it really causes some issues for us. Okay, the other big issue with dusty star-forming galaxies, besides how far away they are, comes from their name. They're really dusty. And so to illustrate how dust kind of messes with us, I like to show this image from the Hubble Space Telescope. So this is the Pillars of Creation. It's a star-forming cloud. And so this is a lot of molecular gas and dust all clumped together. And it's the site of the birth site of stars. So this is an optical image. And so then Hubble actually went back and took the same image, but with its infrared cameras, so at longer wavelengths. And this is what you see. And usually when I do this in a public audience, I get a lot of oohs and ahs right now. So I'm going to pretend that's what you're all doing. So this is the infrared image. And you can see that, I mean, the dust that you thought were these really thick columns of dust that you couldn't see anything through, there's a lot of stuff going on beneath it. Tons of stars. And maybe most importantly are things that you thought were kind of red. I'll go back. Like in the dust, stars that look red would make you think, oh, it's red, it's maybe a lower mass, it's maybe older. And when you look at those same stars, they're a lot bluer. And so then you realize, oh no, these are actually, there's a young stellar population here, but the dust is reddening it and making me think it's older and different than it really is. So dust plays a few tricks on us. So yeah, it blocks ultraviolet and optical light from young stars, which effectively makes observations at short wavelengths really difficult. But at the same time, that dust is heated up by that optical and UV light. It heats up and then re-radiates in the infrared and submillimeter, so longer wavelengths. So that means that dusty things are actually really easy to observe at longer wavelengths. So that's good, and we take full advantage of that. Okay, so back to dusty star-forming galaxies. Thanks to arrays like ALMA, there's a whole bunch of other radio observatories. Spitzer is the space-based infrared observatory. We're able to get a lot of good long wavelength observations of dusty star-forming galaxies. So the general consensus now is that DSFGs are thought to be a specific phase of massive galaxy evolution. So a relatively short period of time compared to the entire lifespan of a galaxy. So we're talking like 100 million years compared to the billions of years that they exist. So it's unclear if most DSFGs are triggered by mergers or interactions like Mambo 9, the work from my advisor that I showed earlier, appears to be, or other mechanisms. And the morphologies are hard to decipher due to observation limitations. So like I showed you all those really cool merger images from before, but what's on this slide is more like what I actually look at on a day-to-day basis. So the far left is observations from ALMA, the array in Chile that I mentioned. This is a galaxy I'm writing the paper on right now. So no one's actually even seen this image yet. But this is from about a redshift 5 galaxy, we think. And yeah, look at it. It's really something. I like it a lot, but other people might not get the excitement. The middle image is also from my advisor's old work. And again, this illustrates the coolest thing about long wavelength observations and why dust is tricky. So the background image, the blue and the red, that's from Hubble Space Telescope. And the green contours on top are radio observations from a radio array called Merlin that's based in the UK. So you see on the left side one, it looks like there's two possibly interacting systems, and the dust, which is the green contours, traces the optical pretty well. But on the right-hand side, the dust, which is the green, is totally offset from the optical. So just looking at the optical, you might think this is kind of a, not that special of a system, but when you add in the dust component, you realize how much you're missing. So for dusty star-forming galaxies specifically, it's really important that we're doing multi-wavelength observations and taking full advantage of the longer wavelengths. Okay, so in terms of dusty star-forming galaxy evolution and what we think are likely scenarios for how they evolve over time, the most evidence we have right now is pushing us towards this story that DSFGs evolve into massive elliptical galaxies that we see in galaxy clusters. So this is the same image of the Virgo cluster, and you can now imagine that all these massive ellipticals here at one point in time were dusty star forming galaxies. They went through huge explosions of star formation for one reason or another, mergers or something else. Once all those stars, supernovas blew up, they've shot out all the gas and dust from around them. Any spiral, any kind of structure was, morphed away. And then you're left with a massive elliptical. And so there are a few things that support this theory. And so one of them is the number densities. So the number of ellipticals we observe locally, in nearby us, more or less matches up to the number of DSFGs that we observe in the distance. So you can kind of say, oh, the same number, they all evolve into the same number. That works out. Another thing are the stellar populations. So the number of stars present that we can infer in the DSFGs and the types of those stars match up with the old stellar populations that we see in local ellipticals. So you've given the stars, billions of years to evolve into the old stellar populations that we see today, and the timelines match up. And then lastly, a thing that kind of supports the scenario is the depletion timescales from cosmological simulations. So you can imagine you have all this fuel, roughly how long it takes to form stars. So the time it takes for a dusty star forming galaxy to use up all of its fuel puts it in line with the age of the universe at which we see these ellipticals. So all these three things coming together makes this scenario seem pretty plausible, and is something that people are still working on to solidify. And so while that seemed all well and good, we thought we kind of understood dusty star forming galaxies. Then, classic universe decided to throw a wrench in things. And recently there has been new developments on a potential missing population of dusty star forming galaxies. So these are referred to HST dark sources. So that means the Hubble Space Telescope, as great as it is, has not been able to detect them. And you could say, oh, well, maybe Hubble just didn't stare long enough at that patch of sky. That's true. But at least for the observations that we currently have, we have cases of sources that show up completely blank in HST imaging, which is what you see at the top panel of this 3 panels of images. So you have the HST, there's nothing there. And then you get into Spitzer, which is near infrared observations, and then you see a sources. The pixels are very big because the resolution isn't very good of Spitzer, unfortunately. But then you get to ALMA, the submillimeter, and you can see a clearly defined blob, which is what we always look for. So these HST dark sources are also pretty interesting because they're less extreme than the DSFGs that I've been talking about. So they still have, star formation rates, a couple hundred solar masses per year. And they exist at redshift greater than 3. So another thing that made this population very interesting, though, is that recently ellipticals or quiescent galaxies have been discovered at higher redshifts than were previously thought possible. Because you imagine, to get these old stellar populations and to get an elliptical shape, you got to give it time to either crash into things and just let the stars evolve. But this new population of higher redshift ellipticals has started showing up. And it's been hard to see them because they don't have those bright optical UV stars because they're red and dead already. So they've been popping up in surveys. And so now the thought is, are these HST dark DSFGs the progenitors for these new high Z ellipticals, in the same way that the extreme dusty star forming galaxies are believed to be the progenitors of our local ellipticals? So these are honestly very new questions. Like this work has just been published in the last year. And it's what I'm looking at right now with my current paper. So it's all very exciting stuff. But I think with that, I will wrap it up in the interest of time. But thank you very much, and I'm happy to take any questions.
Awesome. Thank you very much for that talk. So if you do have any questions, go ahead and put them in the chat. We can ask Sinclaire any of those questions you might have. So one question I have right now is that you had mentioned that these galaxies have some fuel that kind of spurs on the star formation. So what is that fuel that creates these stars?
Yeah, so great question. The main fuel to get star formation is molecular hydrogen. So that's two hydrogen atoms bound together. And generally, I mean, basically, so the image I showed of the pillars of creation, that is a huge cloud of molecular hydrogen, more or less. There's some other stuff thrown in there too, but it's a lot of molecular hydrogen. And if you can compress it enough, get it to cool and then the gravitationally collapse in on itself, it will form a star for you.
Okay. And then we had you have the Hubble tuning fork where you go from ellipticals to spirals, but it seems more like it's going from spirals to ellipticals. What is the evidence that we have for that process? Like simulations or observations? Like what makes us think that that's how these things are forming?
Yeah, basically, kind of like the video I showed, we have evidence, observational evidence of spirals and ellipticals, and then these mergers in between. And through computer simulations, which I wish I worked on, but I don't because I think they're really cool. People do these crazy simulations of basically, yeah, crashing disk galaxies together and seeing what comes from them. And more often than not, you get a nice elliptical.
Okay. And since you are talking about dust, I know astronomers hate this question. Like dust and magnetic fields are like the two questions you never want to get asked. But do we have an idea for what dust is? Like what is dust?
Yeah, this is an ongoing area because, yeah, there's a lot of annoying things about dust. Dust, so we think, I'll maybe add a little more to that question too, on the formation of dust. There are two main formation mechanisms that we think for how we get dust. The first is supernovae. So you've got massive stars exploding, and in that crazy amount of energy, you're fusing, you're having fusion and getting, atoms greater than iron and stuff like that. And from that, you can get these silicates. So we think dust is mostly silicates. And then the other formation mechanism is through, they're called AGB stars. And so when you have a lower mass star, like our sun, for example, when it eventually evolves into a red giant, it'll go through this phase where it starts like pulsating and pulsing out material. And we think dust also comes from there.
Okay. So I know when you can get galaxy mergers, you can also get something called an EGN, where you have a kind of like a quasar, you've got a big black hole in the center, and it can actually generate a lot of light. And sometimes it can be a bit difficult to kind of disentangle the two. Is there a way that, as astronomers, you can tell the light that we see is from star formation or the light that we see is from this EGN?
Yeah, great question. That's also a huge pain to disentangle AGN from star formation. I completely did not talk about even in the diagram that showed the evolution, that kind of square diagram, the right hand corner was on quasars, and I just pretended like it
It's
wasn't
fair,
there. But yeah, so the main way you can do it is again through taking advantage of multi-wavelength observations. So like I said, to look at young stars and find star formation, you might be looking at UV and optical, or doing the dust reprocess light in the submillimeter. AGN can emit insane X-ray radiation, and so people will use X-ray telescopes to look specifically for AGN. They also emit in the mid-infrared, which does cause some problems. Are you looking at AGN emission, or are you looking at older stars? But So generally, yeah, if you can get X-rays, that's really that kind of a nice cut and dry way to tell.
Okay, cool. So next year, fingers crossed, JWST is going to launch. How will JWST be able to help solve any problems or questions we have in this field?
Yeah, so JWST is great off the bat because it's going to be in the infrared, so we can like peer through the dust of all these dusty systems and get higher resolution images and try and maybe get a better sense of the morphology of these distant dusty star forming galaxies. Um, I was gonna say something else great about JWST. Um, oh, just like I was showing how even with the best Hubble time we have right now, things aren't popping out just because they're really faint. And so JWST is much bigger, much shinier, and hopefully galaxies that weren't there for Hubble will be there for JWST.
I think every time you mention JWST launch date, it gets pushed back by another day. So we're continuously pushing this
Yeah.
launch date back and back and back. I did notice that the galaxy you were looking at, Mambo 9, is there a Mambo number 5?
Um,
I
Yes, there
assume.
is.
Okay.
Yes, there is. There was a lot of discussion on the naming of that galaxy. I was on the email thread and it was way too long in my personal opinion. Because we care a lot about our names. But yeah, so Mambo was the name of a survey that had a bunch of these DSFGs. And yeah, Mambo 1 through 8. And I think even beyond 9 do exist. But in the Mambo catalog, that galaxy is Mambo 9.
All right. Do you have a favorite galaxy image or galaxy merger?
Oh, good question. Favorite, it might be more for nostalgia reasons more than anything. It's because the very first project I worked on as an undergrad was on a single galaxy merger between, oh, if I can remember these numbers, NGC 5257 and 5258. And it doesn't have a cool name, it just has the catalog name. But I'll always have those, they'll hold a special place in my heart just because it was the very first astronomy project I ever worked on.
All right. And then last question from Jacob. Would you classify Kate Hudson and Matthew McConaughey as a major or minor merger?
Oh, minor. Very minor. Inconsequential.
I admit I have not seen that movie. Is it worth? Does it hold up to time?
Oh, probably not. It's like probably a great, perfectly trashy rom-com to enjoy on a rainy evening,
All right,
which I get plenty of here in Seattle, so works out.
it's true. All right, thank you very much, Sinclair, for giving us this talk all the way from Texas. We really appreciate it. Thanks.
Thank you so much.
All right, we are ready to start our trivia. So there is a link in the description to the trivia page, so you should be able to click that link and it will take you to our trivia form. And I think with that, I will go ahead and hand it off to Arvin.
Okay, thanks, Michael. Great talk, Sinclair. So I will start sharing my screen right now. So you should all see a nice little PowerPoint title slide here about tonight's trivia. So the way we do this for people that have not been to our in-person events or haven't been tuning in online so far is I'm going to ask you guys a series of 15 themed trivia questions. Tonight's theme is you have to decide whether each of these things that I name is a former constellation or a London pub. This actually turns out to be really fun because London pubs can have some eccentric names and former constellations are also often really confusing. So I will go through 15 of these. You guys have to go to this little hyperlink down here. I know you can't click on it on your screen, but there should be one, I think, in the video description and the comments, and you could also just type this into your browser. So yeah, just fill that out as I go through. I'll go through them a second time after I finish, and then you'll have until the end of Astronomy in the News, which is the next segment right after trivia, to submit your answers. After you submit, I'll grade everything, and then after the second talk, I'll come back, tell you guys the answers, and tell you who the winner was. To motivate you a little bit, we have some fun prizes. So we have Astronomy on Tap State College magnets, bottle openers from the Central Pennsylvania Observers, and Astronomy on Tap State College koozies. Also, sorry, back. For the first time this month, we have some space-themed masks sewn by our good friend Macy Houston. So thank you, Macy. And yeah, the winner of the trivia, we will send out a nice little package with some fun prizes for you. So if you want the prize, make sure you put your email in that last little question on the trivia answer form. We won't bother you with any spam or advertisements, just that email is only if you want the prize. Also, I should mention that if there is a tie for first place at the end of trivia, only 15 questions, so it's entirely possible. If there is a tie, I will decide the winner based on the most creative astronomy-themed team name, and that's a subjective thing, so I have the final say there. All right, so let's get started then. And just for a quick example of how this is going to work, I'll give you a name like this. So for this one, for the example, it'll be Pegasus. This is not a formal constellation. This is a real constellation currently. So the correct answer then would not be London Pub. It would be constellation. But for all the rest of them, it will be something that is no longer a real constellation. So something that used to be a constellation and has been renamed or gotten rid of. It'll be either that or a current pub or bar that is in the immediate London area. So number one, this is the log and line. I had to actually look up what exactly this was. It's an old maritime navigational instrument where sailors would throw this little thing here called a wooden ship into the water and then sail out and reel out the line behind them and then count the number of knots in the line over a set period of time to figure out how fast they were going through the water. And that's actually the origin of the nautical term knots for speed, which I didn't know before, but now I do, and so do you. So number one, the log and line. Is it a London pub or former constellation? Number two is the feathers. Yeah, I'm sorry I can't give you some like nice creative images here because if I just showed you the constellation or the pub, that would give away the answer. So we have a little bit of clip art for these ones. Number three is the Rose and Crown. Is it a London pub or a former constellation? Number four is Herschel's telescope. So some fun facts about this guy. This is a big 40-foot telescope that was built at the end of the 18th century. It was commissioned by a certain King George who was somewhat responsible for a revolution around that time. And it was built by William and Caroline Herschel, which actually made Caroline Herschel the first woman in England to be paid as a professional astronomer back at the end of the 18th century. So was this a London pub or a former constellation? Number five is the River Jordan. This is a river in real life, as well as either a pub or constellation. Six is the Spit and Sawdust. By spit here, we mean like a wooden spit, not nasty things coming out of your mouth, I guess. Seven, Charles's Oak. I didn't actually look this one up, but I'm assuming it's named after a king or something, maybe Charlemagne, I don't know. Number eight is the Queen's Head. There's our good friend Queen Elizabeth. Nine is the Northern Fly. Some more fun clip art. Sorry, guys. Is this a London pub or former constellation? 10 is George's Harp. This was also named after the same King George, responsible for funding Herschel's telescope as well as starting a war. So good for him. Number 11 is Bricklayer's Arms. 12 is 3 tons. I had no idea what a ton was before this, but in keeping with Astronomy on Tap, a ton is another name for a beer barrel or wine cask. Okay, so for these last 3 questions, I will be giving you either, I'll be giving you a name and you have to decide whether it is both a pub and state constellation or neither. So there are some of these where we found something where there's both a constellation and a pub named after it, and some that I just made up for you guys to figure out whether it's a real thing. So the first one is the owl. And in the trivia sheet there, it should ask you whether this is both a pub and a constellation or neither. And if I didn't make the answer key correctly, please let me know and I will try to fix that. Number 14 is the silver fern, after that nice plant down in New Zealand. And our last question here is Michael's Mead, another beer-themed thing for Astronomy on Tap. All right, so I'm going to go all the way back to the beginning now and scroll through these one more time, if I can go make faster. All right, so I'm just going to read off the names real quick and go through these a few seconds at a time. So the first, number 1, is the log and line. Number 2 is the feathers. And you guys will be able to see all the names in the answer key, and you'll have until the end of Astronomy in the News again to answer these. So I'm not going to spend too much time here. Number 3 is the rose and crown. 4 is Herschel's telescope. 5 is the River Jordan. Number 6 is spit and sawdust. 7 is Charles's oak. Number 8, the Queen's head. Number 9, northern fly. Number 10, George's harp. 11 was bricklayer's arms. 12 was 3 tons. 13 was the owl. Remember, these last 3 are either both or neither. 14, the silver fern. And 15, Michael's Mead. All right, so I'm going to hand it back off to Jacob for Astronomy News. But thanks, guys, and we are done with trivia.
All right, before you go, I gotta ask, where did you find that clip art? Because it was all like very similar to each other, and the only clip art I know is like Word clip art.
So in Microsoft PowerPoint, you can insert icons. And so like you go to insert and then you click icons and then you like search up a word and it'll come with like a nice little, very clean, simplistic icon for almost anything. Yeah, and they're actually really nice. It's like all free things to use.
All right, I really like the bricklayer's arm. That's pretty good.
Yes.
All right, so as already said, next up is Astronomy in the News with Jacob Lund, and then after that, we will be grading your trivia answers, so please get those in before the end of Astronomy in the News. So go ahead, Jacob.
Hey, Michael, just a heads up, I can't start my video. I think you'll have to do it for me, potentially.
There we go.
Hang on, now I need to escape because of, I am unable to do this. Hang on. Sorry. Zoom is now.
Oh, stop your share.
Okay, there it is. Okay, yeah. Yes, thank you.
All right.
Okay. Sorry, I thought you'd be able to do it for me and yeah, okay. All right, yeah, so astronomy in the news. So you may have heard about earlier this month, the Arecibo Observatory had a bit of a minor or maybe major disaster and a cable snapped and it shredded a 30-meter gash into the over 300-meter radio dish. And you can see those in the picture there, what that looks like. But repairs are expected, and it will be shut down for a few months, but it's a pretty big disaster. Then similarly, on the disaster theme, we had a close one here in California with wildfires that nearly destroyed Lick Observatory, which is on Mount Hamilton near San Jose, California. And this is a really historic site because it was actually the first mountaintop, or the first permanent mountaintop telescope observatory built all the way back in 1888. Thankfully, though, the firefighters were able to contain these fires, and the Lick Observatory is doing all right. There's a fun little story about the director of the observatory staying behind when everybody else evacuated so that they could help the firefighters based on their knowledge of the mountain. A little more uplifting news, maybe literally uplifting. In the past month, we had the launch of the Mars 2020 Perseverance rover. This launched July 30th, so not quite this month, but about a month ago now. And the goal of this rover is to search for signs of microbial life on Mars. This is part of why we chose the Mars Garita for today's drink. So it's, as I said, it's going to look for microbial life. It has a drill that it can collect core samples and then seal those up in a tube, and just, my understanding is, leave them, and then some future mission can come and pick them up and return them to Earth later. And the US wasn't the only ones launching to Mars. It's busy space travel to Mars this month. Both China and the United Arab Emirates both launched missions to Mars as well during that July 2020 launch window. So if you're thinking of going to Mars, traffic might be a little busy right now. So maybe plan for the next window. But that's all we have for astronomy on the news today. I'll turn it back to Michael now.
All right, thank you, Jacob. As I remember, back in the 90s, when they're doing some maintenance work on Arecibo, they allowed people to film GoldenEye, which arguably is the best James Bond movie ever made. So hopefully we'll get another GoldenEye. We're gonna ignore Daniel Craig. Daniel Craig is overrated. All right, we have our next speakers ready to go from our very own Penn State University undergraduates Grayce Brown and Thomas Nguyen, with the wonderfully alliterative title Spinning Shimmering Stars, A Survey of Space with the Penn State Pulsar Search Collaboratory. So I'll go ahead and hand it off to Thomas and Grayce. Go ahead.
All right. Hello, everybody. I am Grayce Brown, as you heard. I'm a junior here at Penn State, studying astrophysics.
Hi, everybody. I'm Thomas. I'm a junior also at Penn State, and I'm studying astrophysics and mechanical engineering.
Okay, and Thomas, if you could share your screen.
Here we go.
All right. And we are here to talk to you about Spinning Shimmering Stars, a survey of space with the Pulsar Search Collaboratory. We tried to make our title as difficult to say as possible. We're going to be talking a lot about a particularly interesting type of star called a pulsar. So you can go to the next slide. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell. She, at the time, was a grad student at Cambridge. She was looking for quasars with a radio telescope. And she noticed in her data she noticed some scruff in her data, which is that picture down at the bottom right. She noticed the scruff had, it was a pulsating signal. It pulsed at about 3 times every second. And so she went back into her data, even though her advisor told her that it was probably just, interference, because you get a lot of interference in radio astronomy. So she went back into her data, which at the time, all of the data was on paper. So she had miles of chart paper to go through. It took her a couple months, but eventually she lined it all up and she found that it occurred at the same spot in the sky, and it occurred 4 minutes earlier every day, which means that it comes from space. If it comes, that means that it definitely isn't interference coming from Earth. The sun takes 4 hours almost exactly to get to the same point in the sky every day, but the rest of the sky, stars and stuff, only take it only takes 23 hours and 56 minutes, because during the course of the day, the Earth moves a little bit around its orbit around the sun, which is why we can see different stars at different times of the year. So this means that it's not just, you know, some guy driving home, turning on his radio every day after work. She jokingly labeled it LGM, which stands for Little Green Men, which is like, maybe it's, you know, maybe it's aliens, who knows? But then she found more, and other people found more bits across the sky that were pulsing like this. And it turns out it wasn't aliens, it was a type of star called a pulsar. The Nobel Prize was awarded for this discovery. However, it was not awarded to Jocelyn Bell. It was awarded to her advisor, John Hewish, and Sir Martin Ryle, who helped develop the telescope she was using and the data analysis technique. It was a bit of a controversy, but she was pretty humble about it. But she and her advisor were interviewed by the media. However, when they were interviewing them, they asked her advisor about the astrophysics part of it, and then they went and asked her about the human interests portion, which meant they were asking her about her love life, about her hair. When they went to take a picture, they asked if she could unbutton her blouse a little bit. It says a lot about how they treated women in science back then. Shortly after the discovery, she went on a vacation, and she came back with an engagement ring, which said something to her coworkers that she would be leaving, because at the time in Britain, married women did not work, because it was thought that the children would become delinquent if their mother was working. So she traveled with her husband for a little bit and worked part-time, but now she is a visiting professor. She holds numerous honors and awards. She travels and she gives talks, and about 2 years ago, she came here. And as a young woman in science beginning my own search for pulsars, seeing her speak was very special to me. So that's kind of the history about how they were discovered, but what exactly are pulsars? You can go to the next slide. Pulsars are a type of neutron star, which is a star that's formed by the violent death of a very massive star. They are extremely dense, they rotate very fast, and they have a very strong magnetic field. And because of that field, this means that they have beams of light that shoot off of their poles. And so if you can go to the next slide, if the magnetic poles are off of the rotation axis, that means that these beams of light spin around, and sometimes they can pass through Earth, or Earth can pass through the beam. And so this is the pulsing that Jocelyn Bell was seeing in her data. She was seeing this light repeatedly point towards Earth. It's kind of hard to talk about how cool neutron stars and pulsars are without first talking about how they come to be. We can go to the next slide. So stars, all stars, including our sun, exist. They live in a balance between with gravity pushing in and pressure from fusion pushing out. And so stars like our sun exist in this balance for billions of years, until eventually the core collapses into a white dwarf and the outer layers they're like poofed off, which is the top line on this diagram here. However, much more massive stars, the lower line here, can only exist in this balance for a few million years, till their core collapses so quickly that the outer layers rebound and explode in a very high energy explosion called a supernova. If a star is massive enough, the core will collapse so much that it collapses into a single point and it becomes a black hole. However, it's not quite massive enough. The core will only collapse until a neutron star, which in my opinion are very, very interesting, right? Like one of the most interesting objects in the universe. They are quite massive. They're about 1.5 to 3 times the mass of our sun, which, I mean, compared to like, you know, million solar mass black holes isn't very much, but when you see how small they are, not only are they smaller than our sun, but they are smaller than the Earth itself. And if you go to the next slide, they are about the size of State College itself. They exist on a scale of only a couple dozen kilometers across. So it means that they are very, very dense. In fact, they're so dense that we don't really know what their internal structure is. We can make some theories. One of my favorite theories is they named the different possible structures after different kinds of pasta, which I think is amazing. They rotate very, very fast. The slowest pulsar that we know of takes 20 seconds to rotate once. The fastest pulsar, which I believe you may have seen on a slide, spins at 716 hertz, which means that it spins 700 times in a single second, which is kind of hard to imagine something the size of State College spinning that many times in a single second. But why do they spin so fast? It's because of something called angular momentum, which is something that you've probably seen at some point. If you've ever turned on the Olympics and seen figure skaters, they start with if they go into a spin, they start with their arms wide out. And then as they're spinning, they pull their arms and legs in and they start to spin up, speed up their spin. This is because when their arms and legs are spread out, all of their mass is spread out throughout at a very wide radius from their center of mass, from the axis about which they turn. And then when they pull their legs and arms in, all of their mass is much, much closer to their center of gravity. And so because of conservation of momentum, it spins a lot faster. And this is the same thing that happens with neutron stars, except on a, the scale of 1.5 to 3 times the mass of our sun. Because of this spin, the rotation generates a very powerful magnetic field. If you've ever seen the Northern Lights, this is caused by Earth's magnetic field, which is accelerating accelerated particles, and it hits the atmosphere and it makes light. Something similar happens with pulsars. The magnetic field is so strong that it accelerates light along the magnetic field lines, and it produces beams of light that you saw a couple slides ago that spin around and sometimes hit Earth. Because of their massive size and their density, they have extremely reliable timing, which is they are very reliable timekeepers, which is very useful in a lot of data taking. If you go to the next slide, Nanograv is a organization that uses the pulsar timing to look for gravitational waves. Because we know that the pulsar timing should be very, very accurate. If there are differences in time, in the timing between the pulses, we can tell that there's something else happening, and it's probably gravitational waves. Nanograv measures waves on a much larger time scale than what LIGO does. But one person who I've had the pleasure of speaking with personally is Dr. Maura McLaughlin. She's a chair of Nanograv, and she's also a PSU alum, but also founded the Pulsar Search Collaboratory, which my friend Thomas is going to talk to you about.
All right, hello everybody. So I'm going to tell you guys a little bit more about Maura McLaughlin and the organization that she founded, the Pulsar Search Collaboratory. So back in 2007, the Green Bank telescope at the Green Bank Observatory was in need of repairs. So 2 astronomers, Maura McLaughlin and Duncan Lorimer, figured, hey, let's leave the telescope on and let it collect data while we do these repairs. So hundreds of hours of data later, this telescope collected tens of terabytes of data of the sky. These 2 astronomers realized that this was the perfect way to get high school students more involved with STEM, using this data to introduce students to radio astronomy and searching for pulsars. From this data, they made a bunch of prep-fold pulsar plots, which is what you see here, and high school students learned how to look at these plots and recognize whether these plots had the signs of pulsars in them or not. This was a fantastic way to get students excited about astronomy, and the organization's been steadily growing ever since. There's actually been 8 pulsars discovered by students so far, and that thrill of the potential of being a part of history and discovering something important is what really reels kids into the program. And students who analyze enough of these pulsar prep fold plots get to go to a special PSC research summer camp. And there's a lot of cool things that happen here. The students get to sleep in this big bunkhouse. There are talks throughout the week from prominent radio astronomers passionate about the field. The students get to do their own small research projects based on pulsars. They learn how to operate a small 40-foot telescope, and they get to actually operate the Green Bank telescope. And they also get to do a whole bunch of other fun camp stuff too, like take hikes and roast s'mores and all of that. They do it every year around July, so there's always sparklers and a campfire, and it's always just a bunch of fun. And overall, it's really inspiring to a lot of them. In fact, it was so inspiring for one of the students that went to this research camp that he actually decided that this is what he wanted to do for the rest of his life and added this as his second major. And it was genuinely an amazing experience for me. I got to actually operate the GBT and type commands into its console. I could feel the envy of scientists around the world who would have to pay thousands of dollars by the hour to get to do what I was doing. And here I was, just mashing buttons on a keyboard. The talks were all so amazing. All the astronomers had so much excitement and passion in what they were doing. I kind of just fell in love with that sense of community and the field itself. So here I am now, and I was so excited to hear when I came to Penn State that we had a PSC chapter here. It turns out one of the students who had discovered a pulsar, Cecilia, you can see her discovery plot here, was also really inspired by what she was doing and started her own PSC organization when she came here as an undergrad. And now I'm a part of it too, but I haven't really talked about what we do as college students, or what we do here at Penn State. We have all of these high school students getting involved in astronomy, and so this means this is also a great opportunity for us as undergrads to go in there and help spread the word and be mentors to these guys ourselves. As the Penn State PSC, we help organize and attend pulsar-related presentations. Here in the top left, we have Maura McLaughlin and her Gatekeepers of the Universe presentation. And in the bottom right, we had Dr. Reedhead for his presentation on his own experiences in the field. We also got to be with Jocelyn Bell Burnell herself, who was happy to come in and give a similar talk on her own side of her experiences. And we also take annual trips to where it all began, over to Green Bank Observatory, so everyone can get a feel for the beauty and awe of the entire place. Aside from that, we also reach out to high school students and give presentations to high schools, and overall help out with the general mentoring of the PSC. One of the perks of now being a mentor for the PSC is now I also get to be a mentor for the summer camp and see the other side of things. Overall, really fun experience, getting to help inspire students just like how I was, which is a really weird reversal of roles, but I've slowly grown into it a little bit. During the camp, the Green Bank telescope actually needed repairs, and so all of us mentors got to go onto the telescope itself, and that was just an amazing experience. There's absolutely no better time to remember than being on a 485-foot tall telescope to remember your drastic fear of heights. Like, you see how small these trees are in the background? They're really high. We have to go up on this rickety elevator to reach this platform, and on its way up, it got stuck just in the middle of going up. It was just stuck, and my knees would not stop trembling the entire time. Overall, scared for my mortal life, and I would totally do it again. Now, besides the whole mentoring experience as part of the Penn State PSC, we also have some real research experience as part of our chapter, and we'd love to talk about the scintillation bandwidth project that we've been doing. Grayce?
Yeah, so one of the cool things that Thomas and I get to do with the PSC is we're working with a grad student to measure pulsar scintillation. And I know it's a big word, but it's actually what's happening here in this photo. As light passes through the surface of the water, it diffracts. It bends in different directions due to the uneven surface of the water. And so you can see this forms light and dark spots on the ground. And similar things happen with the light from pulsars as it travels through space, because space isn't empty. As we heard earlier, there's dust, there's stuff in the way, and we can, and because of that, it bends the light in different ways, and we can see that and measure it in our data.
All right, so what is all this stuff in space that's interfering with everything? We call this the interstellar medium. Basically what it is all this plasma and gas and electrons and dust out in space, and this interstellar medium, or the ISM, can interfere with signals and data that we're trying to get from space. Since pulsars are so incredibly consistent with their timing, and we don't know too much about the ISM, we can use pulsars to measure the scintillation and figure out more about what's going on. Other people have tried to do this, but this was decades ago, and we found that some of these measurements can be quite off. So we're giving it our own shot with some more pulsars and some potentially better data. And so to do this, we do a lot of data processing of this pulsar data that we have from an Arecibo telescope survey. And there's a lot of technical jargon that goes on with all the data processing that I won't delve into right now. If you want to know more about it, feel free to ask us questions at the end or reach out to us. Just for now, no, it's all to make increasingly prettier pictures that tell us what we want. And at the end of the day, isn't that all that really matters in science? Really pretty pictures of data. And so after we get all this data processing done, our fancy math program analyzes our plots and tells us what the scintillation bandwidth is. And that's the measurement that we've been looking for that tells us how much the ISM is affecting the signal from the pulsars. And with that, we can finally determine more about the properties of the ISM and make our own model of what it's doing. Now, the scope of this project is actually massive. Nobody's attempted to use as much data to map out the ISM as we have. And once we get it all done, there's going to be a lot of extra analysis and research about the ISM based on all these measurements that we're figuring out. So we're really excited to keep up our hard work and see all of this published one day. Right now, we've pretty much got all the kinks out of the system in terms of the data processing. So it's all a matter of time and effort now as we steamroll through the rest of this data. And that's our project for now. And thank you for listening to our presentation.
Awesome. Thank you for giving us this talk. That was pretty great. I'll bring you both back up. All right, so some questions. Again, if you have questions, feel free to enter them in the chat and we can ask our speakers. So one question I have is that you're looking for these pulsars. Are you specifically observing to try to find pulsars? Like, do you go to the telescope, say, I want to find a pulsar, here's my proposal, I'm going to look here, here, and here. Do you do just a blind search the entire sky, or you just kind of go through archival data that already exists and try to find pulsars through that method?
So, Thomas, you can correct me if I'm wrong, but what we do is we go through drift scan data from Arecibo, and I think we did some with the Green Bank telescope as well, just for like the initial search. So basically, Arecibo broke before, and it just stood there and looked up at the sky, and we took all that data. And so what the Pulsar Search Collaboratory does is we just go through that data looking for pulsars. And if we find something that could potentially be a candidate, I believe what we do is we use one of the other telescopes at Green Bank to look at that and to confirm that it's a pulsar.
Okay, so it broke before. Different kind of damage, I'm assuming. Is that right?
I can't remember exactly why it broke. Thomas, do you remember?
I also
A while ago.
It was probably a hurricane. That's usually what gets them.
It's understandable. About how many pulsars do we know about today? Or do we know of?
A lot.
Yeah.
I want to say two. Well, okay, so we're reviewing in our data set for our scintillation project. We got like 200 pulsars. About only, I think, 166 were actually detectable for that. Thomas is looking it up, how much we actually know.
Let's see. According to Google, about 2,000 pulsars are known right now.
It was either
All right,
200
Google
or
knows all. So the pulsars, you're detecting them in radio observatories with Green Bank and Arecibo. So kind of two questions, I guess. Why radio? Why do they pulse in radio? And then the second question is, do they pulse in other wavelengths? Can you see the similar kind of pulsations in optical, infrared, X-ray, or UV, or anything like that?
So they emit in a wide range of throughout. I don't know if every pulsar emits throughout the entire spectrum. There are different pulsars. There are pulsars that emit through radio pulsars, and then there are pulsars that emit through X-ray. So there are X-ray pulsars. They are different kinds of pulsars. There's, because of spin down and spin up rates that, as an undergrad, I don't fully understand yet. They emit in the different wavelengths. But yeah, there are different kinds of pulsars, but even though we are just looking at just radio pulsars, it is still a wide bandwidth, which is, if you were looking in those charts that we see, there were those long vertical lines. And that's how we tell it's a pulsar, because it's emitting in all of those frequencies. Whereas if it was just interference, which is something that we see a lot when we're going through plots, interference is generally only out on one frequency. So you'll see like a bar across the bottom. But yeah, so it is a wide frequency, but generally there are radio pulsars and there are also X-ray pulsars.
And I know there's this phenomenon in which radio pulsars, like they emit in a certain spectrum of the EM spectrum, or in a certain range of the EM spectrum, but sometimes that they can glitch and all of a sudden they emit in a completely different part of the spectrum, and then they just like glitch back. And there's a lot about pulsars that we generally don't know, and how they're like emitting all of these and just changing where they're emitting. And it's all still like being researched and looked at.
Okay, it's just aliens, right? It's aliens that are causing everything. If you don't know, it's just aliens. So you're talking about radio interference, and I know one of the things about Green Bank Observatory, the town that it's in, is actually one of those cities where they have a very strict policy of, you can't have cell phones, you can't have microwaves, your cars all have to be like the diesel engines, no spark plugs. So what was, Thomas, I know you had, I think both of you actually have both been to the telescope, is that correct? So what was your experience going to this town where you couldn't have like any kind of electrical interference?
I've only been there once, so my story will be a bit shorter than I'll let Thomas go. It was interesting. We didn't spend a whole lot of time in the town, but we couldn't bring, digital cameras close to the telescope, so I had to get a disposable camera. You had to have your phone off if you were anywhere near it. There was actually one time where we were trying to take some data and we had some weird readings, and we were like, whose phone is on? The only way that we could contact other people was going into the computer lab and sending an email, logging onto Google and my Gmail. But getting into that, the computer lab is a giant Faraday cage, and so it's like stepping into an airlock. You have to open one door first, step into this like copper container, and then go and open the other door, and then you're in the computer lab. It was very interesting.
And honestly, there wasn't really even a point in bringing your cell phone, because the entire, like a large portion of West Virginia is covered by the National Radio Quiet Zone. And so once you're in that zone, your phone doesn't even get a connection anyway. So it just becomes this brick. You can't, really serves no purpose. You really just kind of get used to it. It's kind of nice to like be outside and distance from all of those electronic distractions and just really take in the beauty of Green Bank, because Green Bank really is really beautiful. I've been there 3 times now, and it's just something I look forward to now at this point. Just really nice and serene.
So one of the photos you had there, like you were on the Green Bank telescope, but there's another dish that was a bit further in the background. So are there multiple radio dishes at this observatory?
Yeah, there's like about 10.
Okay.
Not all of them are being used. I know there's like there's the 40-foot telescope, there's a 20-meter telescope. There are some other telescopes that broke some records when they were around, but I don't quite remember right now. A lot of them were out of operation, but they're still, the remnants of them are still around. They're still really cool to look at.
Okay.
From what I can remember, the only active ones are the Green Bank Telescope, which is the 100 meter, and then there's the 20 meter, which I know that the PSC uses sometimes. And then when we go and during the PSC camp, students get to learn how to use the 40-foot one, which is a smaller one. It's the only one that's not controlled in the main control room. You could actually go into a bunker underneath and move it and take data. But there are a bunch there that are out of commission because they broke or they have no purpose anymore, or like not purpose, but like they're not being kept up.
Yeah, I know funding has been an issue. I think they've had a rally to kind of get funding for Green Bank past few years. So you mentioned that this is kind of a high school project as well. So if you're a high school student or maybe even a college student, undergrad, and you want to get involved into this pulsar search, how might you go about doing that?
Just go on, if you're a high school student, just head on to the Pulsar Search Laboratory website. They have sections for students just on how to get involved and how you can learn to take pulsar data or learn how to sort through pulsar data yourself. If you're an undergraduate,
if you're an undergraduate at Penn State, get in touch with me and Thomas. I'm the vice president of the club this year, and he's the secretary. And we can get you onto the email list. And we meet Tuesdays at 7. And I think the mentor meetings, which is the whole collaboratory you train to become a mentor so you can mentor high school students, is Thursday nights, which will start sometime in October.
Okay. Are there high school students in State College that are participating in this that you know of? Like that you guys are mentoring? Or?
Part of our goal this year is we're kind of transitioning from a mostly research-based chapter to we're trying to get more outreach. We're trying to reach out to more high schools this year, and so we're hoping to get. As far as I'm aware, I don't know anybody personally at State High or in State College that does it, but we're hoping to get more involvement this year.
Okay. Very cool. Well, thank you very much, Thomas and Grayce, for coming out. Really appreciate you giving that talk. Thank you.
Thank you.
Thanks for having us.
Yeah.
All right. We are ready to go back to our trivia answers. So, Arvind, I'll let you take over and show us who won and what the correct answers were.
Sure. Well, hopefully these are the correct answers because that would be a shame. All right, great. So we are back, and here's the trivia again with the answers. Thanks everybody for playing. That was a lot of responses. Yeah, so let's go through these real quick. Number 1, this was the log and line. The correct answer was that it is a former constellation. I was actually surprised that a majority of people got this wrong. I think this is the only question that a majority of people got wrong. But a lot of constellations, especially in the southern hemisphere, were named after nautical and maritime things just because of the time that they were discovered, or like discovered by the Western world, was a lot of the time by sailors who were exploring. So they got a lot of these nautical names. Number 2 was the feathers. This one was a London pub. I think most people got that correct. 3, the Rose and Crown. This was also a London pub. 4 was Herschel's telescope. This was a former constellation. It was down here next to Lynx. I think the stars that were in this constellation are currently part of Auriga and Gemini down here. 5 was the River Jordan. This was also a constellation. I couldn't find an image for it, so I just pulled up Stellarium, and it starts in Canis Venatici and then goes down through Leo Minor Lynx and ends in Camello pardalis, or the camel leopard, which is also a giraffe. Spit and Sawdust. This was a London pub. Charles's Oak. This is also a constellation. This guy over here, this oak tree. Queen's Head. So this was not only a London pub, it was 4 different London pubs with the same name. There were also, I think, 4 or 5 others with like slight variations on this name, but I guess Queen Elizabeth must be very popular. 9 was the Northern Fly. This is a constellation up next to Aries in the Pleiades. 10, George's Harp. This was also a constellation up by Cetus, big sea monster. Bricklayer's Arms. This was a London pub. Nice little weird base here. Number 12, 3 Tons. This was a pub. It was not a trick question. It's named after beer barrels and wine casks, so it's a pub. Number 13 was the Owl. This is both a pub and a constellation. He's over here on the tail of Hydra. Number 14, the Silver Fern. This was neither. I was just having fun. Sorry. And number 15, which is actually my favorite question of the night. This was neither. We actually named it after the mead that Michael, our host here, has been brewing for the last few months to keep himself occupied during the quarantine. So that's all 15 questions. The winner, which was the team Bellatrix's Army, actually got every single question correct. The only team to do that, the only team so far in our virtual trivias at least. And yeah, the team name was not a tiebreaker, but it's astronomy themed enough. So I will send out the information about sending you your prize later this week. So look out for that. And yeah, thanks everybody for playing. Oh, also special shout out to my parents for having the lowest score tonight. Very, very impressed. So yeah. All right, back to you, Michael.
Wow. Wow. That is bold. That is bold to call out the parents for supporting their son and watching astronomy on tap and just throwing them right in the trash. All right. Thank you everybody for coming out tonight. Pretty successful astronomy on tap. We will be back in September next month. So feel free to stick around on our Facebook page, on our Twitter, on our YouTube page. And if you sent in your email onto the trivia forum, we will send you monthly updates for when our next Astronomy on Tap event is. So thank you again to our speakers, Sinclaire, Grayce, Thomas. Thank you to my co-hosts, Arvin and Jacob. Thanks for coming out. We'll see you in next month.